Hey everybody, welcome back to another round of physics. And yeah, let's get going. Okay. So this displayed for you is an electroscope. Let me walk you through because it's a bit hard to see. I'll zoom in later so you can see it a little better. You have a metal sphere attached to an aluminum rod, and off of this hook way at the bottom, although it's hard to see, there are two very thin pieces of aluminum foil. And what's next? Well, I'll go ahead and take a glass rod and the wool, and I'll go ahead and rub the glass rod on the wool. Okay. Now we know that we're separating these charges. And now what I'll do is let's go ahead and touch the glass rod to the sphere. Now remember, the sphere is conducting, so I've deposited some charge onto the sphere. Now because it's a conductor, that excess charge rapidly distributes through the length of the sphere and the rod, and by contact down into these aluminum leaves. And now you see, way down at the bottom, you can see those aluminum leaves have separated. So let me go ahead and pause the video there. Okay. Pretty cool, huh? Yeah. Okay, so now I have a question for you. Okay. Let's say that we've done this in the lab. Okay, we have a very fancy measurement instrumentation, and we've done this in the lab. Okay. And let's go through and see if we can come up with an expression for the force acting on the aluminum leaf. Let's say one of these aluminum leaves. Okay? Let's go ahead. So let's do that. So I'll draw it first of all. Let's go ahead and I'll start off. Let's say that the system is one of those aluminum leaves. Okay? And so for the surroundings, okay, what objects in the surroundings significantly interact with that aluminum leaf? And for sake of argument, let's say that we take the right aluminum leaf, the one that was hanging off on the right-hand side. Okay? Yeah. Hopefully, right? We have, for example, the force of the earth acting on the leaf. Okay? And that would be, whoa, I can't spell earth. That would be through the gravitational force, Fg. Okay? Well, also, yeah, we have this yet to be defined interaction between the aluminum leaf that I have chosen as my system and the second aluminum leaf. So I'll put second aluminum leaf. Okay. And also, yeah, we have the interaction with the hook. Okay, and for lack of a better term, I'll call that like a tension force. Okay, good. So let's go ahead now. Okay, we would like to get an expression for the force of the second aluminum leaf on the first. Okay, so we're trying to characterize that interaction. And so in order to characterize that interaction, we are going to need to get expressions for these other things, right? If we can account for all of the other interactions, then this last unknown interaction must be due to the aluminum leaf. Okay? So let's go ahead. Let's do a free body diagram of our system. And what direction will the gravitational force be acting on our system? Yeah, good. That's going to be acting, we'll say, down towards the ground. Okay, so I'll put Fg here. How about the interaction between the first aluminum leaf, which I've drawn in purple, and I'll put in the other aluminum leaf. I'll draw that in red. So that's the second one. What direction would that interaction be? Yeah, good. We'll estimate it as going to the right here. So I'll put that as the force of the aluminum leaf. Okay? And the force of the hook? Yeah, good. Along the length of the aluminum leaf. So I'll put force, the tension force here. Okay? So next question for you. What's the acceleration of my system? Yeah, good. You saw in the video that the leaf was just hanging there. And so we can make a statement that the acceleration of my system is 0. Well, what does that mean that the net force acting on the system is equal to? Good. Yeah. And what physical concept are you using? Yeah. By Newton's second law, F net is equal to ma, right? If the acceleration of the system is 0, that means that the net force acting on my system must be 0. So we'll go ahead. We'll put that the net force acting on my system is equal to 0. Okay? Good. Now let's take a brief byline. This is just kind of setting the stage, setting everything up. Let's take a brief moment here. Let's say that we're actually trying to do this experiment in the lab. Okay? What pieces of information am I going to have to get in the lab in order to determine, for example, the gravitational force acting on my system? What piece of information do I have to go into my lab and measure directly? Yeah, good. Don't forget the gravitational force, right? The definition of the gravitational force, and I'll put it as a magnitude right now, that is defined as the mass of the object times the acceleration due to gravity close to the surface of the Earth. Okay? So in order for me to actually complete this analysis, I'm going to have to take that little aluminum leaf and stick it on a scale and determine the mass. Okay? So let's assume that we've done that. We have measured the mass of the aluminum leaf. Okay? We will assume that we have that quantity. Okay? So, good. The second piece of information that we're going to need, okay? The second piece that we'll have to determine experimentally, we'll have to put a little protractor up to our glass cage, and let's assume that we have measured, and I'll go ahead and draw this in. Let's assume that we have measured the angle theta, the angle at which that aluminum leaf is hanging at. Okay? Now, why is that important? Why would it be important for us to measure that angle theta? Yeah, good. It'll help us with this tension force. Okay, good. So we will assume that we have that angle theta as well. Okay, good. Well, let's continue on. Okay. So we know that the net force acting on our object is 0. Okay. And now let me ask you, how many unknowns do we have? Thinking about the forces for a second, how many unknown forces do we have? Yeah, we don't have a good definition for the tension force of the hook acting on our system. And we don't have a definition for the force of the second aluminum leaf on the first. So we have 2 unknowns, okay? Which means how many equations are we going to need? Yeah, good. 2, right? We have 2 unknowns. And so we'll need 2 equations. Where are we going to get our equations from? Yeah, good. Don't forget the force is a vector, and therefore I can break that vector into individual components, and looking at each of the individual components, that is to say the x direction, the y direction, the z direction. So I better put an axis here. By looking at the individual directions, we can build up several equations. In this particular instance, 2. Okay? So let's go ahead. Looking at, let's start off with the y direction, the vertical direction. Okay, looking at the y direction, I can write the net force in the y direction is equal to 0. Okay. And what can I write down for the net force? What specific forces that I have in my free body diagram should I include in that expression? Yeah, good, 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 good. So let's go through. We have, put in the vertical here, we have the tension force, but we don't need the magnitude of the tension force. We need the component that's in the vertical direction. And that's why we needed the theta. If we measure theta, the angle that the leaf, our system, is angled at, that tells us the angle at which the tension force is pulling at. And so we can use that angle along with the tension force to get just the vertical component. So I'll go ahead. We'll say the magnitude of the tension force. And you better ask yourself, do I use a sine or a cosine here? Yeah, I need the vertical component, which is adjacent to the angle. And so adjacent means I use the cosine. So I use the cosine of theta. And then we have the gravitational force. Notice that because I have chosen to call up away from the floor as my positive y, I should include a negative sign for my gravitational force because it is not pointing in positive y direction, it is pointing in the negative y direction. And so I finally have an expression. Okay. Now notice here, this expression used for the y direction only has one unknown, the tension force. So I can go ahead right now and solve for the magnitude of the tension force. Moving mg to the other side, I find that it is mg divided by the cosine of theta. Okay, go ahead. Take a stab at the x direction. Got it? Yeah, good, 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 good. So for the x direction, we have F net in the x direction is also 0. We're not accelerating in the horizontal direction at all either. And so now we go back to our free body diagram and we say, well, what forces have a component in the horizontal direction? Well, we have this unknown force, the force of the aluminum, that we're trying to characterize. Okay. Or we could say the force between the charged pieces of aluminum. And that again is pointing in the positive x direction based on what I chose to call positive. Now also we have the component of the tension force in the negative x direction. And now I need this component, the component that is opposite the angle. And so I use the sign. Because it's pointing in the negative x direction, I put the negative sign. We have our tension force. And we have the sine of theta. That picks out the component that's in the horizontal direction. And that whole thing equals 0. Now, of course, from our discussion about the y direction, we have an expression for the tension force. So I will go ahead and move everything. I'll get the force of the aluminum piece by itself, and I will substitute in the expression for the tension force. So I can think about moving this second term to the other side, and I will substitute in our expression for the tension force. So at the end of the day, I have that the force of the second aluminum piece on the first is equal to mg over cosine of theta, right? That's the expression of the tension force, times the sine of theta. Of course, the eagle eyes among you recognize sine of theta divided by cosine of theta is just tangent of theta. So this altogether simplifies to mg tangent of theta. And boom, we're done. By using the electroscope, knowing the mass of the aluminum leaf, and measuring directly the angle, we can infer the force that the second aluminum leaf exerts on the first. Okay? Now, so we have that idea. Okay? Now it's just a matter of repeating the experiment. Imagine for a second that I took the glass rod and I charged it up, say, for half a second. I do the experiment, I measure the angle, and I figure out what the force is. Then I discharge everything. I remove all of the charge from the electroscope. You say, how could you do that? One way is just touch something metal to it, right? If I discharge using, something like a pie plate. Yeah, you see that? Right? By touching the pie plate to the electroscope, I then move charge to the pie plate, and then I can dump it somewhere. I can do it again and dump it, and do it again and dump it. Okay? Generally, this procedure, it would be something, you could do it by connecting the pie plate to the ground. Okay? That dumps all of the charge away. Okay? So then the next thing you could imagine me doing, I charge up the rod for 2 seconds and do it. And I measure the angle between the leaves, and I go through and calculate it. And then I discharge the electroscope. Maybe I do it for a half a second, okay? Or maybe a second and a half, right? So what you really need is some consistent way of getting charge. Now this, of course, this is, very crude, but theoretically it could be done. The length, the amount of time that I spend charging up the glass rod is proportional. That would mean that there's proportionally more charge, which means I deposit more charge on the electroscope, and so that gives you an idea. Cool. Okay, I'll leave it there for the discussion, but keep chewing it over, keep thinking about it, bring questions to class, and yeah, we'll just keep going forward. Hey, I thank you for your attention. Have a good afternoon. Keep up the good work. I'll see you next time.